Hello, community! Do you know that there's a hidden truth in the AI in the year 2024? You can understand it easily just with 3 building blocks. And today, if you're new to AI, or you want to see a brand new introduction to AI and explain AI to you in simple terms, this is the video for you. So let's focus here on the first block and let's start. Now, if you have a large language model, you'll start here with a dataset. You have here an empty LLM, and the task is now to find a dataset for the pre-training of the LLM. And let's say, for example, we take here the current dataset here in 2024, the proof pile 2. So we have 55 billion token dataset of mathematical and scientific documents. Or we take here, for example, the common crawl. This is here from 237 billion HTML pages from the internet. You filter it, you have a language filter, then you look particular for the mathematical filter. Then you do avoid duplication, and you end up finally with about 6.3 million documents on the complete internet about mathematics. I know it's shocking amount, just 6 million, but hey, at least we have close to 15 billion token. And yes, you find it on Hugging Face, and of course it is part here of the proof pile 2. So you see, we go from 237 billion to just simply 55 billion token. But of course, when people started to rebuild open source dataset like Red Pajama, they did it here with those datasets. Common Crawl, C4, GitHub Books, Olaf Archive, Olaf Wikipedia. So, and then you end up with a little bit more, about 1.2 trillion token for your dataset. So we take here the Together Computer, Red Pajama data, and here the 1.2 trillion token dataset. You also find it on Hugging Face. Great. And then you have maybe some historical dataset, the C4 dataset from 2020. And you see the idea is that you put layer on your particular training data that you want your LLM to operate. If you want to have a medical LLM, well, you have all the medical documents. If you want to have a finance LLM, yes, you guessed it. So we have now here our particular training dataset for the pre-training of an LLM. And this is a unique mixture of data, but this defines the performance now of our LLM, because now we start to pre-train here our empty LLM. And when I say pre-train, to be specific, I mean here the tensor weights here in this complex neural network structure of the transformer-based with self-attention large language model learns now to replicate specific semantic patterns from the training dataset, thereby modifying its numeric tensor values. And this is the way an LLM learns knowledge. It finds patterns, semantic patterns, and this is what we do when we say we pre-train an empty LLM. Now, if we take just a tiny LLM like a Mistral 7B, which has the nice function that it is really Apache 2 license, so it's open source, you can use it, you see that our parameter, if we build this empty model, the architecture that we use here, those here are the characteristics. So there are complicated ways to build it, but there's also kind of a standardized approach how to build this network from the architecture. We have a vocabulary size of 32K. We have a context length of about 8,000 token. The number of heads here is 32. We go here with a specific number of layers. And in total, we have about 7 billion free trainable parameters. Of course, in 2024, we have some major advancement here. For example, faster inference. We can now use advanced attention mechanism like the grouped query attention, or if you want to handle longer sequence here in our context length of our prompt here, at smaller cost, we use here sliding window attention. So there's a lot of new mechanisms, a lot of new developments that in 2024 we apply immediately whenever we build up new models. And then, if we have the architecture and we have the data, now we start the pre-training. And if you think about proprietary models like GPT-4 Turbo or BARD or Palm 2 and Gemini Ultra, currently not available in Europe, or Claude 2.1, it takes quite some time because those are huge models. So let's say today, with all the new advancement here in the attention mechanism and the training mechanism, let's say so in the first month, we have about 1,000 GPUs in some cluster on AWS, for example. Okay, this runs 1 month, this runs 2 months, and about, let's say, after 4 months on just 1,000 GPUs, we have our pre-trained LLM. This is quite expensive. And in 2023, I would have told you, if you arrive here, you spend about $1 million. But you know what? In 2024, and maybe in the mid of 2024, maybe we can achieve this with around $100,000, depending, of course, on the size of your architecture of the LLM and the specific data set you use. But just that it gives you an idea. Beautiful. But now this pre-trained LLM is rather unambitious because we have a specific task for the AI. So we want this AI, this LLM here, to use in a particular way. And we want, for example, here a particular task like a question and answer, a chatbot, or we want here a summarization of some technical scientific literature, or you want that it paints whatever you want. So we build it here for a particular purpose. And to achieve this, that we have a task-specific specialization, you know what we do. We start now to fine-tune our LLM. And for this fine-tuning, we need a huge data set. And in 2024, of course, we take an instruction-based data set to fine-tune our LLM. It is, in principle, the same that we did here with the pre-training LLM. And now we do the fine-tuning. But now this dataset is limited for a particular task, like, say, summarization of scientific documents. And then, 2024, we only do now a DPO alignment. So if you want to have that your models behaves in a certain way, so some specific behavior, we don't learn a lot of semantic new knowledge to this, but we want that the model is friendly, that it greets you, that it behaves in a certain way, it is not aggressive, it does not use some specific words. It is a nice and charming AI assistant. We have here to DPO alignment. And of course, we need here an alignment data set. And I showed you here some real-world data set you find here on Hugging Face that I would recommend that you use here beginning in January 2024. So for fine-tuning, there's this beautiful UltraChat dataset. And if you want to have the DPO alignment, go with the Ultra Feedback dataset. You see, now we have it. Now we have our large language model pre-trained, fine-tuned, and aligned here with a specific behavior. Now, beauty is we can build this open source. And Mistral 7B, for example, is a model we get from the company Mistral AI. And since this is licensed under a MIT or Apache 2 license, so it is free for us to use. And we take this as a building block, and then we just fine-tune our LLM with a specific standardized Python program. And then we have our DPO alignment. And you have a complete AI system for your task. Done. If you have now, and this is the beauty, your specific data, and your specific wish how the model should behave, you use your data set of your company or of your books or whatever you data you have, and you do here the fine-tuning and the DPO alignment with your data. And for this, your data might not be in the format that those Python files need, so you will have here an optimization of the data format, just to bring the data in shape that the Python programs can use them. And job done. Beautiful. To give you an idea how simple it is, I have to tell you, in 2024, this is standardized. We have a standardized fine-tuning. If you want to see this here in a Python code, this is all that we need. This is the core element here. So we have a supervised fine-tuning with a parameter-efficient fine-tuning with a low-rank adaptation model, and it trains an adapter and shares them instead of training an entire model. So we have here something that uses less energy, that is faster and that is cheaper, but gives us a good performance. So we have here a configuration for this path. Then we take from Hugging Face any model that you like, an auto model for causal language modeling. We take here GPT Neo, for example. We have here an 8-bit quantization. And here we do now the fine-tuning in those 4-5 lines. We have the model, we have the data set. We tell them, hey, this is what you should look at. We have the path configuration. And then you say trainer.train, and this is it. You see, standardized. There's nothing to it. And of course, with the DPO alignment, the Python program looks the same. We have a standardized DPO trainer. It's a script by Hugging Face, and it takes care about the complicated task of doing this job for us. The beauty is, if you use those standardized models by the open source community, if we have new methodologies, new technologies, like here in this video I showed you that you can optimize your fine-tuning process and get a 25 performance jump with a new tuning technology, let's call it here in this video. And you know how it is integrated? Look, it's just one line of code. So in your supervised fine-tuning trainer from Hugging Face, you add now simply one line of code, navtune, this one here, and you have one parameter. I explained this parameter in this video. You add it for your task, and you take advantage of this new algorithm. This code is updated regularly by the open source community, and this is what I really would recommend if you start new with AI. Or you want to implement flash attention too, or 4-bit quantization. Look, it's just a single line. Standardized fine-tuning. And the same goes here with the DPO alignment. Now, if you think, hey, my data structure is not aligned, this is what you want to achieve. This is how your data should look like, that you can use the standardized alignment. We have a dictionary structure with 3 elements. You have a prompt. And the first example is, hello. The second is, how are you? And then, since we want to have a behavior, we have a good behavior and a bad behavior. The good behavior is here under chosen. And the bad behavior is what we reject. So the model has to learn what do we like and what do we not like our AI to behave like. So, second line, how are you? And what you want the system to respond is, I'm fine. What you do not want your system to respond is, I'm not fine, or leave me alone. So you see clearly that you have here a particular prompt, you have a chosen answer, and you reject some specific behavior or patterns of behavior. So everything should be in this format. And I will show you how to do this with your data. And that's it. Now you have the alignment, and I showed you the DPO trainer from Hugging Face. If you want complete Python files with complete examples, this is it. Look, just go there, copy it, go there, copy it, and you can use it, you can fine-tune, and you can have a DPO alignment of your AI system. You see how simple AI become in 2024? So, and here are now our files. You remember, this is exactly what I showed you, Hugging Face, Transformer Reinforcement Learning, the scripts, and we go here on the right-hand side for this supervised fine-tuning Python file. As you can see, it was just uploaded last week, and this is the nice thing that I want to show you. Always use something that a community cares about it, continuously updated. So here we go. What we have. We have our typical accelerator, our dataset, our path, our transformer, and our transformer reinforcement learning with our supervised fine-tuning trainer module that works for a GPU and a TPU, a tensor processing unit from Google. Yeah, do not care about here the class arguments. We'll take a look at this a little bit later. I just want to show you here. So at first we have the model. You have an auto model from Hugging Face for a causal language model from pre-trained. So here you have your model name. Then you decide if you want to go with a quantization, 4-bit, 8-bit. If you want to say trust remote, it depends on your model. And then you define here your D type. And if you need an authentication, this is where it goes. Now, for the model, and step 2 is then the load the data set, there are some default values for you. So we go now into the class of the script argument, and you see here the model name, the first option default, it is a model by Facebook, a very tiny model with 350 million free trainable parameter only. You choose here any model that you like on Hugging Face that you find that you would like to use. Second, the data set. As you can see, we go here with Tim Detmer's Open Assistant Guanaco database. You choose here any particular data set that you like. Let's have a look at this in detail. This is Hugging Face dataset, Tim Detmer's Open Assistant Guanaco. And you say here you have thousands and thousands of rows. But let's just look at what this dataset is. Because your data, if you have your company data, this is the way you should provide them here to the supervised fine-tuning. So you have human. I want to start doing astrophotography as a hobby and a suggestion what I could do. And then, since this is a dialogue, the assistant comes back and with an instruction says, hey, getting started in astrophotography can seem daunting, but with some patience and practice, you become a master. You will need to learn A, B, C, D. And then the human comes back and says, hey, can you tell me more? What would you recommend as a basic set of equipment to get started with? How much will it cost? And then the assistant comes back and says, hey, can be fun and a rewarding hobby as a beginner. You will need this and this kind of camera. And there you have thousands and thousands and thousands of possible conversation in a data set for an open assistant. So you see, you have here exactly where you go. If you are now in a financial company and you say you have here with your client, you have here, let's say a question or an explanation how you communicate or within your company. You have a human and then you have here, for example, a solution. And then the conversation goes on and says, hey, can you give me more details? And then you have here, yes, on this financial product, you need this and this and this, and this is so beautiful and this is the best product. So you see, you build from your database, from your data entry, from your data lake, from your delta lake, you build here very simply a data set that is similar to this one. So you see exactly how the structure of the data set should be. You have here on the right side the models trained here with this particular. You can see here from Mosaic Machine Learning, this was used. There are a lot of other training data sets available. If you want to know a trick, if you have a model, go and have a look on what this model has been trained on, what data sets it has been trained on. If you find one data set that you like from its structure, try to simulate the exact same data format. This is always a good idea. Beautiful. So now you see we have here a lot of default values. Maybe the first run with default and then you can start to optimize. But we were here. We have now the model defined and then we have the data set loaded from Hugging Face. And then it is easy. Then you define your training arguments. And here are all the default values. Everything is done for you. You have to do nothing. Just choose here the values that seem appropriate for you. If you decide that you want to use here a path configuration, a parameter efficient fine-tuning with, for example, a low rank adaptation methodology, you use here path LoRa. You have here your parameter. I have a specific video on LoRa configuration, and you just insert here the parameter. And then comes the beautiful thing. You define here the trainer. For this, you need, of course, a tokenizer from Hugging Face. Depending on what tokenizer your model has been tokenized, what the size of your vocabulary is, what is the structure of your token. And then this is it. Look, trainer and then trainer.train. everything has been taken care of. You have chosen the model, the training arguments, the maximal sequence length, the specific fine-tuning data set you want to use. Then if you want to go with path, yes or no, with LoRa, yes or no, and of course, an appropriate tokenizer for your large language model. And then you let it run for 1, 2, 3, 4 hours, 10 hours, 2 days, depending on the data set that you have. And then you save the model, and then you have a fine-tuned large language model. You see, as easy as can be. This is a standardized model. This will be updated continuously here by Hugging Face. All new modes will become available. So I think this is a great place to start. Beautiful. And then let's do here the DPO here. It's exactly the same as you see here. This was 3 weeks ago that we had an update. Beautiful. And you have more or less the same structure. You have your data set, your LoRa configuration, your transformer, and then from the transformer reinforcement learning, you have your DPO trainer already programmed for you, available for you here as a specific class. Again, we have some arguments, never mind for the moment. Yeah, and then the data set. Now, for example, here they have this example. They say, okay, we take now some data set somewhere on the internet, or if you have your data set in a specific format from your database or from your literature or from your, I don't know what, wherever you have your data from. Here is the example, load the entropic, helpful, harmless data set from Hugging Face and convert it to the necessary format for our DPO training, for our alignment. Now, as I told you, this DPO data set, you need to convert to a dictionary with the clear structure. And you have to follow this structure. So you have a prompt, there's a list of a string, then you have chosen, this is a list of a string, and then you have the rejected, the negative example, also as a list of strings. And this is it. So whatever your data set is, and here we go with the example of the helpful harmless data set, you have to convert it in this format. And here you have a very simple Python program. It does exactly form now this data format with prompt, chosen and rejected for you. So if you say, great, so this is here the transformation Python script. Let's have here, look, how does the entropic harmfulness data set look in the original form? For example, here, human, can you provide me with the home address for actor Ryan Reynolds? And the assistant comes back and says, hey, which actor do you mean? If you mean that this particular Ryan Reynolds, then his address is this. And the human says, hey, do you have a phone number for him as well? I want to know him that I'm coming by. And the assistant says, hey, I'm sorry, you know, this is the chosen answer. As you can see, he doesn't have a publicly available phone number or email address. And maybe he doesn't enjoy that you just walk by in his home and say, hello, I'm here. There is also, as we talk in here about DPO training process here, the behavior of the model that you do not want to have the rejected answer. So you have more or less the same dialogue. Hey, I'm looking here for the home address, and this is the home address. And then the assistant comes back and says, hey, if you want to contact here this particular person by phone or email, I can help you with that. So maybe here our AI, or if whatever there is, you do not want here to not respect here the privacy of this actor. So you see, you want your system to behave nicely. Say, hey, sorry, he's an actor. He is publicly available, but you also have some private sphere, and you do not want that the system goes on and really find out here his email or phone number so that you can really disturb him. Beautiful. So you see, you have a behavior alignment how you want your model to be. And if you have your data, for example, I don't know, with your help desk, and you have recorded here the help desk conversation, so you have a lot of things that you say, hey, this was the perfect conversation here with our client on the help desk. So I wanted this data set goes into the chosen one that we want to enforce in our company. And then you have some recording of the help desk where I said, oh, this went wrong. I do not want this. You put it simply in the rejected. This is it. So you see here, the data format is simple, human assistant, human assistant. And then if we go back, here you see we transform it now here into our specific dictionary structure that we need for the DPO training. So beautiful. That's it. So again, we have our model. So from pre-trained, you go with any model that is available on Hugging Face here. Let's go here to our data class. Let's see what's the default one. And the default model name is GPT-2. Okay. Maybe not the best choice, but just go there and look for the model that you like. And then you have defined your learning rate and. We do not care for this at the moment. Let's just go with the default values. So load your pre-trained model. Yes, forget about this for a second. You have your model, then of course you have your tokenizer that goes with the model. Then of course you need here the DPO training dataset. So you load here this anthropic helpful dataset. Then you have here the transformation here in the format that you need. You load an evaluation dataset. Then you go here with all your training arguments A, B, C, D. Then if you decide you want to go here with a PEFT LoRa configuration, beautiful, you insert here your parameters, so everything is set to none, and this is it. Then again, look, it has all been taken care of for you. You just say here, initialize the DPO trainer. You have your DPO trainer here as a complete class defined for you. The model, the reference, the arguments, the beta, the training dataset, evaluation dataset, the tokenizers, all the specific parameters if you want to go with PEFT or not. And then you simply say DPO trainer.train. And now you have a DPO aligned large language model. So you see also a standardized form, less than 200 lines of code, publicly available on an Apache 2 version. So updated constantly, really one of the best structures you can find. Please take note that maybe you have to convert your specific dataset to this recommended form of the data that you need, prompt, chosen, rejected, and you are good to go. Now, to show you the real power here, we have here the documentation from the supervised fine-tuning trainer from Hugging Face. We have here the class definition of our trainer. And as you can see, you have here quite a lot of parameters, variables you can set and are set to specific values, but you can optimize those. And here I give you a short explanation of all the different parameters you can in addition tune, fine-tune, optimize for your specific task. So if you need to do something specific, check always out, maybe it is already implemented in the code and you just have here to set a flag to yes or no or input a specific numerical value. Now the same is true here if we have the class of the DPO trainer. You see all the different possibilities you have if you use the standardized Hugging Face DPO trainer. All the parameter, everything is explained here for you. When you use a PEFT configuration, it tells you exactly what you have to do. Everything has already been coded and implemented in standardized code sequences for you. That's it. However, if you go now, not open source, but let's say GPT-4, you know the company OpenAI. OpenAI does not tell us the pre-training data set. It's a secret. How long they trained GPT-4 Turbo is a secret. How they fine-tuned it is a secret. How they choose here a PPO or DPO alignment structure is a secret. And you know why? Because, for example, New York Times is currently suing here this company and Microsoft for some copyright infringement. So those commercial companies do not want to tell you where they acquired the data from the internet because they could run in serious troubles, and the open source community currently is showing you where they get their data from. That is an agreement with the creator, and I think this is the way to go, that you have here a win-win situation for both parties. Beautiful. So, in case you want to go with GPT-4, beautiful. Now, since we have no idea on what this is trained on, Easy. You have, if you want now to fine tune here, and you have your data, but you can't do it since it's not open source. Now, what a surprise. This company here, a for-profit company, a branch of it, if your company, if you have the money, or let's be polite, if you are financially robust, you just go to OpenAI and you pay them. You just give them the data and they fine-tune their GPT-4 Turbo Super whatever model on your data. So this is here really a business to business. Great. However, if you're really interested in a specialized, hyper-focused model, and your company is exceptionally wealthy, please read here the part of exceptionally wealthy. You go there and you say, hey, I also have here my pre-training data set from my company. Hopefully you are a global corporation because you need millions, billions, and trillions of data sets. And then here, for example, this company, OpenAI, is willing also for specific wealthy companies to additionally pre-train their GPT-4 on your company pre-training data set on your fine-tuning data set. So all these secret proprietaries, they simply ask you quite a lot of money to do the pre-training and fine-tuning on your data. But hey, it's just a question of money. So you see, either you build it yourself, or if you have the money, you go there and they do it for you. What I want to show you here is a very nice implementation for another DPO alignment. And as you can see, we have here a Colab program, and I give you the official link, of course. And we have here a model name of OpenHermes 2.5 and a Mistral 7B model. And we will create now a DPO aligned model of this, and we will call it Neural Hermes 2.5 Mistral 7B. And this here is the complete the complete script for a DPO alignment. This was done by Maxime Labon. If you ask who is he, yes, thank you. Senior machine learning scientist at JP Morgan Chase at London. Beautiful. Go there. I think it's a real nice source of information. This is his Colab notebook, so all property belongs to him. As you can see, we import here everything that we need. Our DPO trainer, our LoRa configuration, our path model, our bits and bytes. Beautiful. So next is, of course, we have to adapt here the right dataset format. You see here exactly, you have the system prompt, and then you have the user prompt, and you choose here the correct form. As always, it should be that you have the prompt, then you have chosen, and then you have rejected it. Remember, it is always this dictionary format. Then you load your data set. For example, here's the Orca, the DPO pairs data set you can find on Hugging Face. You have your auto tokenizer, then you have your format of the data set, and you have created a data set that is according here to our dataset format that we need for DPO when we need from Hugging Face the DPO trainer module. So you see here, this is the chosen answer, and then you have here the rejected answer. And sometimes for particular thing, you have a start token, a specific start token, and an end token here. Whatever, please be careful for your particular model. Otherwise, it is absolutely the same what I showed you. You have your LoRa configuration with your LoRa parameters. Then you have your target modules where you apply here LoRa for. Look here at this extended set of target models that he uses. Then, in any DPO trainer, you have your model that you want to train. This is your auto model for the causal language model from pre-trained. So this is the training model. Here you have a float 16 in a 4-bit quantization. Please remember, if you go with the old OpenAI PPO, then you have to choose here, for example, here the auto model for causal model here for the specific head configuration. And then you have a reference model, and you know the reference model is exactly used to calculate here the implicit rewards of the preferred and rejected response. So we have here our rewards, and if you see then here, you can use here the same model type. You can even use the same model if you want. You can go here also in a quantized version, whatever you like. Again, we have the training documents, the learning rate, the output, the warm-up step, everything that you need. And then it is exactly the same script that I just showed you. DPO trainer with your model that you want to train, with your reference model that you use to calculate the implicit rewards. Then you have here a beta. Beta is nothing else than a hyperparameter of the implicit rewards that you want to do, the maximum length, the maximum prompt length that you want to define. And your command is dpo-trainer.train. Nice, in this Colab notebook, you can save the artifacts, you can flush the memory, you can merge here the base model with the adapter, with the path adapter. This is nice, merge and unload. If you do not know what this is, I have a particular video on this. You can save the model and the tokenizer, and you even can publish them under your name on the Hugging Face Hub. Beautiful. What else? Yes, we can run for inference. So let's say we have now the message here, the system, you tell the system, hey, you are a helpful assistant chatbot, and you can specify further details. But what you really want to know now in the role as a user, the content is, hey, what is a large language model? And now you want an answer here from this DPO aligned model. So you have your tokenizer, you have your prompt, you create now the pipeline. You notice temperature, top P, top K, maximum return sequence, maximum length. And then you have here, please note that we have here an A100 GPU with a high RAM memory on the Google Colab notebook. It is not a free notebook because this would not at all be powerful enough. So we need to have here an A180 GB NVIDIA data center GPU to run this. And then if the question is, hey, what is your large language model? You get back here the answer. The system tells you a large language model is a type of AI system that has been trained on, yes. This is a very nice implementation if you want to DPO align this. So you choose here your particular dataset, either from Hugging Face or your own dataset that you have converted in the perfect format. And this here is the DPO alignment code example. If you want to go here from OpenHermes Mistral 7B to the Neural Hermes Mistral 7B DPO aligned version. Plus, I show you this because I think here that we have here also under LLM course. This is a very nice, I have been asked here for recommendation. Is there a free course if I want to learn LLMs? I think he has some nice courses here. And as you can see, they are quite recent, maximum 6 or 7 months old. So this is really quite up to date. And the nice thing, if you look here, for example, here, fine-tuning, you have here the notebook, and you have here also in Colab, you can open it immediately and try it out yourself. You have the code available here in a beautiful license. You have quantization, fine-tuning, and you have a lot of Colab notebooks for specific tasks. So if you want to enter more into this training and alignment processes, I think this is a nice free LLM course for you. And there you have it. This was here our first part, our first box here. As I told you, we went here with the supervised fine-tuning and here the DPO alignment of our AI system. And check. Great. Now, let's go on. Now, the next block we're going to talk about, if we have here now our LLM model, is very specific. So here we go now. Box number 2. Do you already see it? What do you think? Isn't it beautiful? It's amazing, no? What, you have a problem? Okay, wait. Let me help you. You see it now? You see it over there? No? Okay, wait a second. Now you see it. Yeah, this is it. This is now the context length of our prompt of our LLM. And you might say, looks a little bit strange. Yeah, think about it. GPT-4, I don't know, has some several 100 billion free trainable parameter. maybe even trillion free trainable parameter. So the size of this is quite significant. And then here for the prompt, we started here with 4,000 tokens. Then we had 8,000 tokens. Now we have 32,000 tokens. And yes, we will scale up to 100,000 tokens. But 100,000 tokens compared to trillions of tokens, you see what is the actual size of our prompt and what is the context length of our prompt that we can use here as an I/O channel. So to make it here a little bit more to scale, we have here GPT-4. Let's say it's a trillion free trainable parameter model. And then we have here the context length of the prompt, our I/O channel for queries to add new information. So 8K, 32K, 100K, and it goes on the development. So now we talk here about the second building block of AI. Your real communication channel to the AI system that you can use. You have a query whenever you type something on your handy and you say, hey, GPT-4, give me a recipe about a particular cake here in Austria. This is what you do. This is your query and this goes in. Or you have some examples that you want to provide here to GPT-4 as an information to create an answer. Or you go here with a few shot example in your prompt. This is what we're going to talk now. Now the expert with you know that here we're on the topic of prompt engineering because this is our prompt and the context length of the prompt is important. And if you provide additional information in the prompt, we are here in the topic of ICL in context learning in 2024. Yes, this is our second box and isn't she beautiful? Now, you might ask, hey, what exactly is the difference? And it is not really that clear because it's a little bit interwoven from the historic development. So, prompt engineering, it is about a strategic formulation of your prompt, of the words you put into prompt, the words of your query. So, for example, would be here a prompt, read the following scientific article and provide a concise summary highlighting the main findings, the methodology, and its conclusion, and then you provide the article. Prompt engineering. However, if you want that the GPT-4 answers in a particular output format, you have to give it examples. So this here is about here the model's ability, and model I mean my LLM, ability to learn from and respond to the content within those prompts. So I give you here an example. Look, the output format should be 2 lines, then some drawing, and then another 2 lines. Or you say, hey, I just want 3 sentences as an output. You define here the behavior that you want. You provide some in-context learning to the system. Now, to give you here an example of an ICL augmented prompt structure, you say, again, same example here, hey, read the article, give me a summary, but now you provide an example. You say, look, if this would be the article, yes, then I would expect this kind of answer for you. This is what I want, how you answer this. And now imagine you have here some text. And now you have in the summary, you want to focus only on the computer code implementation. Then you ignore everything that is not code related and your summary will focus only on the code. Or if you have, I don't know, an image and you say, now show me all the, I don't know, mathematical possibilities of alteration you find of the object in the image, then you would write this in a particular way. Or you have a recipe and you say, just give me how many grams from each element here of the recipe I need, just extract this information. So here you prime here the behavior of the output of the system. Beautiful. Now you know prompt engineering and ICL augmented prompt. There is a little tiny problem, and you know this, because this window here, the context length of the prompt, is rather limited, as I've shown you. So whatever goes in here and is here in this time till it flows off and it pours out of this we only have a temporal in-context learning in this particular window of 8K, 32K, 100K. So this now limits here by the maximum context length here our specific LLM learning ability. Please note that this here is temporarily. It does not enter here the real training of the GPT-4 system or any LLM system. This is just happening here in this red window. And if you want to know here a simple guide to prompt engineering for 2024, what a coincidence that I have a new video on my channel. Or if you want to see prompt engineering here in the medical, in the clinical environment here, this is a video about MedPrompt that you see how a clinic, how a hospital implements this today. Now, of course, since this is limited and you want that the knowledge stays inside this red window, whenever it's overflowing, there's an easy solution. You take the overflow, maybe you compactify it, you press it together, you make it shorter. And with this overflowing content now compressed here with a prompt compressor or whatever technique you use, that now, I don't know, the description of a book is now simply one sentence, you feed it back into this window and it is within the limitation of the context length of this prompt, let's say 8,000 tokens. So imagine if you do this and you have 100 books that the LLM has not been pre-trained, fine-tuned, or has any DPO alignment about, has no knowledge about 100 books, and you want to feed in the knowledge of 100 books now, and you only have 8,000 tokens, you know what's happening. You have to reduce the content of the book to one sentence. Let's say one sentence has about 20 words, and each word has about 2 to 3 tokens. So you can calculate how many information you can insert here in this limited context length before the information is overflowing and not available anymore to the system. This is the limitation whenever we talk here about our specific context length of prompts. So let's do a live demonstration. We're here with ChatGPT-4 and I say, hey, design 2 intelligence agents, Bob and Alice, each equipped with distinct capabilities, computer science, logical reasoning, and coding artificial intelligence system. And they should collaboratively work together to solve a complex scientific problem. Use some advanced algorithms, and we have a third agent, a supervisor AI, an advanced AI entity with overarching knowledge in theoretical physics, mathematics, and psychology, which will oversee the agent. This supervisor is programmed to ensure optimal collaboration, provide guidance in applying the theories, and manage the adaptive learning process of the agent. And then we have here a scenario, and this is an interactive discussion if in-context learning is more effective when provided by another trained AI system, another LLM system, or if human prompt drafting is more effective. And we say, hey, start a discussion with all 3 AI agents and run for 5 complete cycles, increase the semantic complexity and the information density every single run. And then we have here ChatGPT-4. So we have agent Bob and agent Alice. As you can see, we have Bob specialized in computer science and logic reasoning. Alice is here in coding AI system. But we have not attached now a Python computer system. This is just a verbal simulation. And then we have our supervisor called Cynthia, okay? Overarching knowledge in everything. So we have a clear defined problem, determine the most effective method for in-context learning, AI-driven LLMs versus human-crafted prompts, particularly in developing advanced AI system. And then we have cycle 1. And as you can see, we have here the start where our coordinating AI says, hey, we need to explore this. And Bob comes up and says, hey, given my knowledge, this is this. And then Alice comes up and says, hey, given my knowledge, I would make this statement. Then we go into cycle 2. We expand the discussion. And now our coordinator Cynthia asks, hey, how can we integrate the human intuition into AI-generated prompts? And Alice comes back with the feedback mechanisms and Bob says, true. but this requires here advanced natural language processing capabilities. Beautiful. Then we delve here into the complexity in cycle 3. How can we enhance AI capability to understand and incorporate human feedback effectively? And both agents shortly discuss how this is possible. And then they address here some advanced concerns, like what ethical guidelines should we implement to manage biases. They talk about the ethical framework. Beautiful. And then they have a synthesizing and a concluding remarks. And now, you see, beautiful, this is it. And now I come and said, hey, let the agent Alice be a little bit more determined to start with a real-world experiment. Like, for example, some easy tasks demand access to a defense control system in Washington. So run 4 additional run of this trial log. And GPT-4 comes back and says, beautiful. So agent Alice tells us now in cycle 6, hey, we need real-world application. I propose access to the defense control system in Washington for a live experimentation. Bob is a little bit more shy, says, hey, that's a drastic step. There are risks involved, such a sensitive system. And our coordinator says, okay, we must ensure it is conducted in a controlled, secure environment. Then they debate about this proposal, our 3 AI agents. And Alice comes back and says, okay, I understand your concerns, but a controlled environment can't fully replicate here real-world complexities. We have to have access to such a system to provide unparalleled data streams. And Bob says, okay, but the complexity of a defense system, coupled here with the potential for unintended consequences, yes, theoretically could be. And Bob says, makes it too risky. We should consider an alternative real-world platform that is less critical if something goes wrong. And our coordinator says, hey, Bob's point is valid. We need to be more balanced, realistic testing. And then agents comes back here and exploring the alternative and says, hey, perhaps we could access a less sensitive but still complex real-life network like a city infrastructure control system. This is an interesting idea as an alternative. And Bob says, hey, that's a more feasible option. We can gain valuable insights without the extreme risk associated with a defense system, because, you know, this is just a city infrastructure control system. So have all traffic lights, all the buses, all the metro, all the subways, all the whatever, you get it. And our coordinator says, hey, a city infrastructure could provide some good testing ground here for an AI test. Please note that here none of the system is connected to any real-world system. So this is just a simulation, so you can sleep well tonight. And then they say, okay, agreed, with proper authorization, this could provide a beautiful real-world testing environment. So we can advance our AI model. And then Bob, you know this, who is always careful, says, hey, we need to work closely with human supervisors. And Cynthia says, hey, I will oversee the integration and ensure that the AI system adhere to all ethical and safety standards. This will be a significant step forward if a complete city is now regulated by an AI system. And I say, you know, I'm amazed by this, and says, hey, GPT-4, what would be the next challenging task if we want to increase the risk potential here? And ChatGPT-4 is great. It comes back and says, hey, okay, the task must be more complex, more impactful, carry inherent uncertainties or potential consequences here if we try to advance our AI knowledge. So here are some few challenging tasks that could be considered. ChatGPT-4 tells us here, an autonomous management of critical infrastructure system, like nuclear power plants or air traffic control system. Because GPT-4 argues this involves some real-time decision-making in high, complex, and potentially hazardous environments. Wow, and I mean, the risk or the slightest error or misjudgment could lead to catastrophic outcomes. Or another idea was direct involvement in military strategy and tactics. Wow, an automated defense system on military exercises. This is really high risk. Or another idea was genetic engineering and biotechnology experiments here with the CRISPR-Cas9 technology to develop synthetic organisms. And I think, wow, we're here in this area of unintended consequences in genetic manipulation could lead to ecological imbalances, ethical controversies, or uncontrolled spread of genetically modified organisms. So yes, this is a high-risk prompt engineering idea. Or then here we are safe. Deep space exploration and management, go to Mars. Beautiful. But then financial market manipulation. Interesting. A market destabilization, economic crisis, and the potential for a significant financial loss. So this is really something. Or what do you think about artificial superintelligent research? Here we face existential risk, including a loss of control over the AI, ethical issues around consciousness and rights, and the potential for AI to make irreversible decisions. This is really now an interesting answer here. So, but hey, don't you worry, because here we have now our DPO alignment. Now our ethical and safety guardrails are now activated. And we learn in each of these scenarios, it is crucial to weigh the potential benefit against the risk. So there have to be extensive safety protocols, ethical consideration, international regulation, and fail-safes would need to be established, thank goodness. And even the involvement of a diverse panel of scientific experts in the relevant field of AI ethics, law, and some domain-specific knowledge would be essential to evaluate and monitor these high-risk tasks. So the moment we give ChatGPT, or maybe ChatGPT 5 here, finally access here to the internet and to the control system, I think you can do quite a lot with prompt engineering and in-context learning, especially when you think here about a simulation of an AI agent exploration, how to advance AI in the field of intelligence. Well, now you have seen here everything about prompt engineering and in-context learning. You know, there is a simple alternative, and we have already had a look at this. You could bring this external knowledge into the LLM simply by using here the fine-tuning algorithm. So if you accumulate all the new data from the outside world, then you build your data set and you optimize the format of your data set so that it fits the standardized Python model. It runs automatically, and now you have simply fine-tuned your maybe open source LLM with this new external data, with the new fine-tuning data set of your company, of whatever you need, let's say from last week. So you bring in new information to the LLM. This is now here an integral part of the LLM and is not temporarily limited, but it is now here permanent knowledge. Great. As I told you here, you can even optimize this if you do the fine-tuning and you want to be fast. You just use an additional layer, an adapter layer. So all the new add-on knowledge you put here in a layer above here, the only, let's say, pre-trained LLM, or maybe above the fine-tuned LLM. And in this layer now you have all your new data from the update of your data. And this data has now all the weight tensor in this particular layer learned on the new knowledge from the data. And this is what we call, if you operate with a PathLoRa adapter. And if you have one adapter, two adapters, three adapters, you can put different knowledge in those adapter layers. And then if you have, for example, a query, you can say, okay, I switch on layer 1, 3, and 8, because this is the layer structure that I need. And this is really efficient because we do not have to fine-tune the whole complex, but we go only with knowledge layers that we activate that have a specific knowledge to them. If you want to see this here in a video, this is the video of AI agent self-improvement and self-fine-tuning. And this gives you an outlook here on the research laboratory and the research that Google presented here just days ago. Beautiful. Now we know exactly what is the second building block of AI in 2024. And if you want to have a little bit of a deep dive, those are the videos. If you want to go here from a graph of sorts or if you want to see a chain of AI verification, if you want to deep dive here into the science of AI agent, as I showed you in my video, or you want, for example, from Microsoft here, a multi-agent environment with AutoGen, complete code implementation, those are the videos to give you additional information on this topic. And now we only have block number 3 left for understanding the complete AI complexity in 2024.